Assalamualaikum warahmatullahi wabarakatuh. My name is Hajurani binti Mahbubi. In this video, I'm going to explain about the effect of the ideal filter. So in this video, we are going to use FFT function to obtain frequency domain signal of the wave file. We going to apply an ideal bandpass filter that use a frequency from 300 Hz to 3000 Hz. So basically, this is coding. So before run the code, first thing I think a most important thing to consider it is the state of our wave file. This is a wave file where before we read it, we need to change the mode of the audio from stereo into the mono state. This is because if the wave file in the stereo mode, if you run the code, it still can execute the code, but the graph won't show at the at the select, and it will make also the Scilab become crash. So change the stereo mode into the mono mode first before we run the code. It's very easy to convert. We just use in my case I'm using Audacity to convert my wave file. We just open the wave file, and this is basically my original wave file that is currently in a stereo mode. And if I want to change into the mono mode, I'm just go to tracks and go to stereo track to mono. The Audacity will change it for me. So this is currently the mono state of the audio signal. So after that, we can start reading the signal. And at the first line, after we read the signal, I put a play sound of the why I put play sound here, because I think some people want to play the sound when run the code, but I put it as just as a comment, because this is just want to play sound and it is not required in the assignment. So after that, I just go to use this calculation, plot my graph of audio signal. This line where I plot the frequency at the x-axis, and this line is use an amplitude data to plot at the y-axis. At the line 11, this is where I use an FFT, a Fourier transform, to convert to obtain a frequency domain signal of my wave file, of my mono mode wave file. One very important information that I found when I'm using this coding is I use the absolute in this function. My laptop become hang several times and my Scilab crash, and this is the result of using this absolute function. My laptop, my background desktop become black, and I think that it's really not good to use an absolute function when want to perform a Fourier transform in the wave signal. So I decide to delete the absolute function. Then my code, my Scilab is not crash and my code can run smoothly. So after that, this is where I start to plot my graph using the previous data. Um, this this is very important because it even though it just only the matter of to label the graph, but it is make it make the graph be more understandable and information content, because if we put the of the original the graph and we use label at the y and x axis, the graph is more interesting and more understandable graph. So there I put a title of my graph, that is the original signal waveform, and the label of the x and y axis. So I plot my original wave signal that has been converted into frequency domain. I then plot an ideal filter using this calculation. So in this task, we are required to use 300 Hz to 3000 Hz of frequency only. So I put 300 and 3000 Hz as the range, and I'm using a rectangle function because as we know that for ideal function in the theory, it's a square wave uh, waveform type. So I'm using a rectangular function to plot the ideal filter. So this is the same as the previous. It just plot the graph and use a type and label the x and y axis of the graph. After I plot the sound signal and the ideal filter, I multiply the original sound signal and the ideal bandpass filter to obtain the filtered audio signal using this function. One more important information that I found, that when we want to use a multiplication, we need to make sure that we use a dot before we put the star multiplication, because if do not put the star, when I'm not put the star at my previous coding, if I'm not use the dot in my function, the graph won't appear in my when I run the coding, the graph will not appear. Just the label of the x and y axis in the title that will appear in the graph, but no plot of graph will appear. So this is considered as, and if we do this, it is considered as in as inconsistent multiplication. So we need to put a dot before the star so that the multiplication is being used correctly. So after I multiply the two signal, that is my audio signal and the bandpass ideal filter signal, I can get my filtered audio signal using the multiplication function. And I make it a comment when I want to do an inverse Fourier transform of my filtered audio signal, because it didn't require in the task submit the inverse filtered signal. It just want to show the original and the filtered signal. So I just put comment in my code. So that is over of my code, and when I run the code, this is basically what will I get. So this is my original waveform that I use the data that I explained earlier. So this is what I will get when I plot the graph, and this is the ideal bandpass filter that I get when I create using a rectangular function and range from 300 to 3000 Hz. So this is the bandpass ideal filter. When I multiply my original signal and this bandpass filter, I will get this resulting filtered signal of my audio signal. So this is what I got from multiplying my original, and this is my ideal bandpass filter. So this is the resulting wave. So